Hello, everyone, and welcome to another lesson for contemporary math. This lesson will be over section 5e and relating to correlation. I say we just jump right in. A major goal of many statistical studies is to determine whether one factor causes another. Can you find a cause and effect relationship between two variables? We will discuss how statistics can be used to search for correlations that might suggest a cause and effect relationship. And this word is important, suggest. They might suggest a cause and effect relationship. Moving on, a correlation exists between two variables when higher values of one variable consistently go with higher or lower values of another variable. So with these three examples here, there is a correlation between both of the variables. So one of the variables is a height of people, and the other variable here is the weight for people. And so it is generally understood that as height increases, so does weight. You can think of a little brother, or a little sister, or a little cousin, or a little niece and nephew. They're all smaller than you as an adult. And so we can say that generally, as the height increases, so does the weight. And we can say it the other way. Normally, if you weigh more, you are taller. So this would create a correlation between these two variables. And in fact, this is a positive correlation because as one increases, so does the other. We say they are moving the same direction. They are both increasing. And those are the same for the rest of these here. Demand for apples and price for apples. Those are the two variables for the second example, and as one increases, so does the other. So if the price increases, that means demand is going up, also increasing. Or as demand increases, so will the price. Same thing with this last one. The two variables are practice time and skill. So as one increases, the other one probably increased as well. These are all positive correlations. A negative correlation is when one of the variables increases while the other decreases. So they are not moving in the same direction. One's going up, one's going down. So establishing a correlation between two variables does not mean that a change in one of the variable causes a change in the other. So you may have heard correlation is not causation before. It just means that there is a pattern. It doesn't necessarily mean that one causes the other, even though that's what people like to jump to. It only might suggest a cause and effect relationship. All right, so scatter plots. Scatter plots are how we can look at a graph and see if there's a correlation. So when we look here, and I want this to be known here because we have this information in front of us, both variables here, the production cost for movies and the gross receipts for the movies are both quantitative. They're both dealing only with numbers. So when we have only numbers, we put one of the variables along the horizontal axis and another variable along the vertical axis. And honestly, it doesn't matter which way. This axis could have just as easily been production costs, and this axis could have been labeled U.S. gross receipts. They could have flipped. So what does this mean? Each point over here, each point represents the values of two variables. So let's just take Dark Knight Rises, for example. The x-coordinate of this kind of looks like it is about, what, 250? So that is telling me production cost. The production cost for Dark Knight was about 250, and that's going to be in $1 million. Let's see if I'm right over here. Where is there? Dark Knight Rises. Oh, look at that. 250 million. Yep. All right, so let's take a look at the other part of this this point here, the y coordinate. Looks like it is about exactly 448 million. That's the y value. Oh yeah, look at that. The other value over here for the Dark Knight was 448 million. Look at that, right on the nose. I can't believe I got that exactly right. But one thing you'll want to notice is that by looking at this graph, these dots are just sort of scattered all over the place. It doesn't look like there's a pattern at all. So we would say there appears to be little or no correlation between the amount of money spent producing the movie and the amount of money it earned. And if you've been around as long as I have, you know that spending $500 million on a film does not necessarily mean it will make that much money at the box office. So here's the example of that. John Carter. And if you remember that film, may God have mercy on your soul. So John Carter, a lot of money was spent to make John Carter. Not that much money was made though. Only $66 million were made in the U.S. Whereas, say, Avatar here, Avatar had a big budget. Let's see if we can find that. Avatar, $237 million to make Avatar. But at the time, through 2012, it had made $761 million. So there doesn't seem to be a pattern here. You can spend a little bit of money on a movie and make a lot, like the Marvel Avengers, or you can spend a lot of money on a movie and make a little bit, like John Carter. So since there's no pattern, we say there's no correlation. On this slide, we have a couple more examples of what correlation looks like. And so we have this scatter plot. We don't have the tables here to represent the data, what's going on. But it looks like we are comparing the weight in carats of diamonds to the price in American dollars. So consider this scatter plot, the weights in carats and retail prices of 23 diamonds. So this is important. There should be 23 dots over here somewhere in this graph. The dots clearly show an upward trend. Larger diamonds generally cost more. As prices increase, the weights increase. Or, as the weights increase, the prices increase. And you can kind of see that. See that there's a pattern. You can almost see that there's a line sort of following through this pattern right here. And if the line is going up from left to right, we would say this has a positive correlation. Just as I mentioned, if both variables increase, then it has a positive correlation. Now this one's a little weird. If both variables are decreasing, we have to go right to left to see that. The carats would be getting smaller, the price would be getting smaller, then it's still a positive correlation. A different way to say this is this line has a positive slope. It is increasing left to right. So if the line is increasing left to right, positive correlation. Let's take a look at this third example really quickly here. We have life expectancy versus infant mortality. Oh, that's a very cheery topic. All right, so the scatter plot for the variables life expectancy and infant mortality in 16 different countries, and luckily they're all labeled for us, so that's nice. It shows a clear trend, but this time it is what we would say a negative correlation. The two variables tend to change in opposite directions. When one increases, the other decreases. So if I were to draw a line through this information, it looks like it would start up here and sort of just pattern its way down to the left. So if a line moves down from left to right, we would say that is decreasing. And if it's decreasing, we would say it has a negative correlation. So let's take a look at what's happening with this line. If I travel from left to right, it's decreasing. We know it's a negative correlation. But take a look. As I move this way, the infant mortality rates are decreasing. Like the infant mortality rates are going right to 0, which is nice. And the life expectancy is increasing. It's going to the right. It's getting bigger. If we travel the other direction, I guess this is the bad direction here. As I move up, you can see the infant mortality rates are getting higher and the life expectancy is getting lower. So while infant mortality rates increase, the life expectancy decreases. So they're moving in different directions. The only other thing that we can talk about with correlation here is the strength of the correlation. And the idea is, if you draw a line through these points, I don't know, something like this, you can tell that since it is going up left to right, that there will be a positive correlation. But we would call this a strong positive correlation. And that's because most of the dots here are very close to this line, right? We have one exception over here, but most of these dots are very, very close to this line that I drew in there. Whereas if I draw a line over here through this information, looks like it would be like this right here, you can still tell that it is a positive correlation, but these dots, you can tell here, are much further from the line. So we would call this a weak positive correlation. And then you can see here, in perfect correlation, all data points would lie on a straight line. So if we had a graph like this, and I just had one dot, another dot, another dot, another dot, another dot, this would be a perfect positive correlation because all of those dots are on the same line. And we could also have negative correlation. I'm not sure why there isn't an example of that here, but here's one. If I drew a line through those points, this is what we would say has a perfect negative correlation, all the blue dots there, because they all land on the same line. And that concludes the lesson for section 5E. Good luck.